everyone. This is 3.4 concavity and second derivative test. Alright, so let's go to the first definition of concavity. Alright, the first one is say the graph of f is concave upward on I if the first derivative is increasing on the interval. Increasing means the first derivative is greater than 0. Alright? The second one said the graph of f is concave downward on I if the first derivative is decreasing on the interval. Alright? Now I'm going to combine the first definition and theorem 3.7 together. Theorem 3.7 said that let f be a function whose second derivative. Now you have to take the second derivative and it exists on an open interval I. If it's greater than 0 for all x in I, then the graph is concave upward. If it's less than 0, then the graph is concave downward. And if it's equal to 0, it's just a linear. So the line is neither concave up or concave down. Alright, now let's look at the example from the graph. Look at the example A. The graph is increasing, x is increasing, and y is also increasing. This is graph is increasing and is concave upward. Then from the definition, it said that the first derivative is greater than 0, and then second derivative is also greater than 0. Alright, second example, f is increasing but concave downward. Because f is increasing, we know that the first derivative should be greater than 0 and the second derivative should be less than 0 because it's concave downward. The third one, the graph is decreasing and concave downward. Because the graph is decreasing, we know that the first derivative will be less than 0 and the second derivative will be less than 0 because it's concave downward. Now the last one, the graph is decreasing and concave upward. So because it's decreasing, the first derivative will be less than 0 and the second derivative will be greater than 0 because it's concave upward. Alright, let's look at example. Alright, let's look at this example. First, I'm going to take derivative of this function by using quotient rule. So I use the quotient rule, denominator times derivative of numerator minus numerator times derivative of denominator over denominator square. Alright, next step, I'm gonna distribute the 2x into this. I would have 2x to the cube minus 8x. That's the first term, right? Distribute the 2x in here. I will have 2x to the cube plus 2x. The denominator remains the same. Next step, I will distribute the minus in, right? I would have 2x to the cube minus 8x minus 2x to the cube minus 2x over x squared minus 4 squared. Alright, next step I'm going to simplify this. So the 2x to the cube minus 2x to this cube reduce. Then I have negative 10x over x squared minus 4 quantity square. So that is my first derivative. Alright. Next step I'm gonna take the second derivative of this. Alright. So let's say second derivative of this. Alright. I'm gonna use the quotient rule again. Alright. So I'm gonna have denominator times derivative of numerator minus numerator times derivative of denominator. So derivative of denominator, I would have 2 x squared minus 4 times 2x. I bring the 2 up front, alright, the degree become 1 and the derivative inside. Everything all over denominator square. It becomes x to the 4th. Alright. From here, I have two terms. One is over here, one is over here. Now they share x squared minus 4. I have 1 here and I have 2 here. Alright. So I'm going to factor out x squared minus 4. Now look at the first term. I factor out x squared minus 4. I will left with x squared minus 4 because I have 2 of them. And minus 10. That's for my first term. Right? Now my second term, if I factor this out, I left with negative 10x, 2, and 2x, so negative 20, so negative 40x. Square. Alright? And the denominator remain the same. Right? Now I'm going to reduce x squared minus 4, so this become the third power. Right? So I would have negative 10 x squared, I distribute negative 10 in here, plus 40, plus and plus, minus and minus become plus, 40x squared over x squared minus 4 to the cube. Right? I can simplify some more. This become 30 x squared plus 40 over x squared minus 4 to the cube. So this is my second derivative of a function. Now let's look at the graph. Alright, let's look at the graph of this function. We just take derivative of a function and the first derivative and the second derivative. Alright, the first derivative, if it's positive, then we know it's increasing. If it's negative, we know it's decreasing. The second derivative, if it's positive, we know it's concave upward. If it's less than 0 or negative, we know it's concave downward. So let's look at the second derivative here. You have 30x squared plus 40. When you have x squared, it doesn't matter what x is, it's going to be positive. So the numerator will always be positive. Alright? So we cannot make this equal to 0 because denominator cannot be 0. If denominator is 0, it's undefined. So there's no way we can make the numerator 0 here. So at this point, the second derivative cannot be 0. Alright? And if you look at x, when x is plus or minus 2, it makes the denominator equal to 0, which means the function is undefined. Alright? So look at the graph, you're going to have an asymptote here, -2 and 2. Alright? And the region break it down into first, second, third, and fourth region. Alright? We're going to test all of them. Alright? Let me try the first one. The first one is anything less than -2. So I pick -3. -3 in this region. Plug it in the first derivative test. So you're going to have -10 times -3 over -3 quantity square minus 4 the whole thing square. Alright, obviously I'm just gonna look at positive and negative here. Alright, negative and negative is positive on the numerator, denominator, anything square is positive. So I know it's positive. So it's positive. If the first derivative is positive, it is increasing. So I know it's increasing. Alright, now let's look at the second derivative. I pick -3 as well. -3, I'm going to have 30 times -3 square plus 40 over -3 square minus 4 quantity to the cube. Alright, and if you simplify this, it's going to be positive. Alright, it's going to be greater than 0, so you know it's going to concave upward. So it's going to concave upward. Alright, so in this region, it's going to increasing and concave upward. So your graph should look like this. Alright, the second region is between -2 and 0. You will do the same thing. You're gonna have, I did use -1 for the first derivative, and it's turned out to be positive. Alright, you can check this yourself. For the second derivative, I used -1 as well, and it's less than 0. So it's gonna increase but concave downward. It's gonna increase and concave downward. So it's gonna be something like this. Alright. And the third region, I use 1. So f prime of 1, or first derivative, is less than 0. So it's decreasing. But if I take the second derivative, f double prime of 1 is concave down as well. So my graph should be something like this. And again, my 2 and -2 is just the asymptote. Alright, my graph is not perfect. Alright, now the last region is 2 and above, but I use 3. F prime of 3 is less than 0, so it's decreasing, which means the graph is decreasing. For the second derivative, is greater than 0, which means it's concave upward. Concave upward. Alright, so my graph should look something like so. Concave upward and decreasing. Alright, see you next video. Alright, let's look at the next definition. The definition of point of inflection. Alright, a point of inflection of the graph f if the concavity of f is changed either from upward to downward or downward to upward at that point. Now look at theorem 3.8. Alright, to find the point of inflection, you have to take the first derivative and then the second derivative, then set it equal to 0, or the second derivative does not exist at x equal to c. Now this theorem is if then. Alright, so if you have this is then, the reverse is not true. Alright, now let's look at example here. I have a function f of x, so first I'm going to take derivative of this function. So f, the first derivative will be 3x squared minus 12x plus 12. Alright, I'm going to take the second derivative of the function. The second derivative would be 6x minus 12. Alright, then I'm going to set the 6x minus 12 equal to 0 and solve for x. Then I'm going to get my inflection point. So if I have 6x minus 12 equal to 0, 6x would equal to 12, right? X would be 2. Alright, so let's graph this. I have a number line. Number 2 is over here. Alright, I have two regions on the left side and on the right side. So on the left side is negative infinity to 2, on the right side is 2 to infinity. So I'm gonna let my second derivative at, this is 2, so I can pick 0. Yes, that will be easy for me. Yes, pick 0. So 6 times 0 minus 12, that is minus 12, which is negative. So it's concave downward. Alright, on the right hand side, I start from 2, I can pick number 3. Alright, then I have 6 times 3 minus 12, which is 18 minus 12, which is positive, so it's concave upward. So 2 is my inflection point. Now I have to get the y coordinate because I have a point, I need xy coordinate. So I'm going to substitute 2 in the f of x function. So f of 2 is going to be 2 to the cube minus 6 times 2 squared plus 12 times 2. Alright, if you solve this, you should get 8. So the point of inflection is 2, 8. Alright. Hi everybody, let's look at our last theorem. This is an alternative of the first derivative test. This is the second derivative test. Alright, you have a function and f prime of c equal to 0, solve for c, and the second derivative of f exists on an interval containing c. If you take second derivative and at c, and if it's greater than 0, then you have relative mean. If you take second derivative at c and it's less than 0, then you have relative max. However, if you take second derivative at c and it's equal to 0, the test fails. So you have to use the first derivative test. Alright, let's look at the example here. Again, we want to find the all relative extrema. So I have a function here, degree 3. First thing I'm going to do, I'm going to take the first derivative. So I'm going to have f prime of x, alright, equal 3x squared minus 6x. Alright, That's the first derivative. You set it equal to 0, alright, and solve for c. In this case, it's our x. So I'm going to set it equal to 0. So I have 3x squared minus 6x equal to 0. I'm going to factor out the GCF, which is 3x. I left with x minus 2 equal to 0. Alright, two terms multiply each other equal to 0. So either 3x equal to 0, x equal to 0, or x minus 2 equal to 0, which means x equal to 2. Alright, this is my c here. Alright, next step I'm going to take second derivative and plug in my c. I have two of them now, 0 and 2. And if it's greater than 0, it's relative mean. If it's less than 0, it's relative max. If it is equal to 0, then I have to use the first derivative test. Right? So let's do that. I'm going to take second derivative. Right? So from here, I would have 6x minus 6. Right? Then I have to plug in the 0 and then the 2. Alright? Let's plug in the 0 first. So I would have 0 times 6, which is 0. This is negative 6. This is less than 0. So this is relative max. Alright, and if you plug this 0 in here, your y will be 3. Alright, so relative max will be at 0, 3. Alright, let's plug in 2. Then I'm going to have 6 times 2 minus 6, which is 6 is greater than 0. It's greater than 0, so it's relative mean. Add x equal to 2, substitute 2 in here, alright? You're going to have y equal to negative 1. So that's your relative max and relative mean. Alright, I'm sure you can do all the homework for 3.4 now. So see you next time. Bye.